did everything out of necessity. I see where things are going. I seen where they were going before the branded years started. Okay.
Yeah.
And, you know, going back to my channel here, Brad, make a long story short, you can get typecast. When my channel took off on the wood gas stuff, it got real big real quick. I was like, oh wow, okay, this is getting interesting. You know, I'm having people, even when I go out sometimes locally, will go, hey man, are you the wood gas guy? And or I called into a radio show, and I'm not going to say which one it was. I'll say he's the one that people have what's the good way of putting it, censored and totally got rid of him.
Yeah.
And
Yeah.
9/11, an inside job. This could be one of his T-shirts he sells, but I will not name the unnamed one. But I called into that show one day and had people reach back out to me,
Right.
because they recognized my voice from the videos. Goes, hey man, are you the wood gas dude? And I didn't call myself Flash when I called into the show, and
Right.
and that kind of was kind of scary. I had a couple people reach out and go, dude, I recognize that voice. You're the wood gas dude. And I'm thinking, okay, yeah, I guess I am. I'm the Tin Man, you know. I don't know.
Yeah.
But so I realized then, I said, man, I knew the channel had a lot of people viewing it. And buddy, since Brandon took office, this channel has come back to life. It's hopping again. I'm answering
Right.
questions every day on this. But
Right.
everything I've done was out of necessity. Going back to the typecasting, when I started my channel off, it was with electronics. Then I wound up doing the wood gas. That thing, I did a couple years of running doing that. And then I started doing other stuff, man. I went on to other projects that I was working on, including setting up solar. And boy, you would have thought, like, what was it, Bob Dylan, when he went to acoustic to electric? Everybody's like, oh, I hate you. You betrayed us. You know, I don't know if you know that story, but
yeah, I remember that. Yeah.
okay, well, it was like that. I was like, and I people come up saying hateful stuff to me. I was like, you get over it. I said, this channel is not about. I said, that's just, I wear many hats. You know me, man. That's the way I've always been. It's, you know, if something captures my attention, I'm gonna follow it to the end. Which I want to go back to something we talked about earlier here in a second that doesn't have anything to do with this. Yeah, I mean, I started doing stuff for the solar because I knew that to be independent, and I had to have more than one avenue for power. The solar, which right now I'm now officially set up, barely, but I'm really off grid with everything. I can sit here and I can go off grid at will. Just go outside, flip the power over, and so I'm running about 8 to 9 hours a day, running the house off grid, all the small stuff. I can't run the heat pump or the electric stove, but that's going to be converted over to propane as far as the stove goes. And if I had to, I could run window units. And this is off the baby system. I built up a small system, Brad, a while back to run my shop with. I took my shop off grid a couple years back and immediately seen $35, $40 difference in my electric bill. And about a couple of weeks, well, actually, today's the 4th day that I finally set it up. But I've had all the solar panels to be able to double the power on the shop. I've had them for years and just haven't done anything with them. Well, so I finally sat down, and a week ago, I finally set it up, doubled up the panels for my shop, and realized, hey, man, I got enough power here to run the house and the shop with the sun shining. I got a transfer switch set up. I can flip over and run off a generator, or the solar in my case. But the gasifier, and for any of you out there that are going to be watching on my channel, all this stuff's hand in hand. If I had a whole bunch of rain days, solar's not going to do me any good. And if things go really far south, well, guess what? I can crank up that wood gasifier. It's there. It's on the go. It's ready to go whenever I need it. And I can make it run every time because I've got the feel on this thing, and I can make it happen. And I'm always going to have power here. And that's, and it's being self-sufficient. Not only that, hold on, this chair collapsed on me. Not only that, I upload garden videos to my channel. People like tell me, what the hell is this? Now, granted, a bunch of people get it, and a bunch of my good friends that do wood gas, they're like me. They're preppers, buddy. Gardening, canning, everything else. And I always grew gardens, man. I've grown gardens since I was uh, 12 and 13 years old, man. It was a family thing. But, you know, I got back about, well, in 2017, when I was in that accident and I was out of work for all that time. Yeah, I started gardening again. I never quit. And I've canned stuff. We've canned stuff here and put it back. So this is all about not having to depend on anybody else. Then people need to get that into their mind. Everything has a reason and a rhyme to it. You know, wood gas, solar panels, gardening, um, it all comes together and it all meets at a central point. You know what that is?
Independence.
Independence, covering your backside. That's absolutely right. I'll shut up here,
Yeah.
man. 'Cause I can rumble until I lose breath.
No. Like I said, man, I mean, we've been on the air how long so far? About 30, 45 minutes?
About 41 minutes. So I'll keep going if you want to.
Yeah, I tell you what, let's take a little break. We'll go ahead and do a part 2. We're going to break this down. So, you know, because we did the gasifier, and I think on the next one, we're going to discuss some of the other projects that, you know, we've worked on together, you know, and kind of give people an idea. Okay, this kind of stuff, this is just a couple of, you know, Southern boys in a no-name town, just, you know, piddling around, coming up with, you know, the kind of things we've done. So it's been interesting.
I can see you laughing because if people only freaking knew. I will leave it at that, man.
Yeah, I'll leave it at that too. Those are good days. I missed it. Yeah. But anyway, so
people have no freaking idea. All right, we're gonna pause here.
Yeah. Go ahead and you can go ahead and shut it off, and we'll do a part 2. All right. Well, we're back here for part 2, and you know, we spent the first part of this show talking about the gasifier, and I thought, what the hell? We'll just tell people some of the things that, you know, we kind of worked on in the past. One thing that really I thought was intriguing, and you know, I was the guy that was getting all the parts for you and whatever, and you explained it to me, and hell, I even got a journal that I kept on this project. Here's about this thick, and I would go over and over again trying to, you know, why does this thing appear to be doing one thing, but in reality it's not? You know, we didn't know that at the time. We were trying to prove that this thing was actually, I guess as you put it, a very efficient power supply. And I went through everything, and I finally broke down. I kind of, in a cryptic way, without giving away the entire show, I wrote to a website that had electrical engineers on the thing, and I explained basically what this was. And they said, "Oh, that's the capacitor paradox." And they sent me like 2 or 3 papers that people had PhDs on this. And the capacitor paradox, well, I tell you what, let's let you tell everybody, what is a capacitor paradox there, young man?
Well, apparently, the power in a capacitor, if you charge one up, look at it like a bucket of water. You put 5 gallons in it. Okay. Technically, you could run that capacitor into another capacitor that was totally discharged and run that through a load while you're doing it. And let's say you started off with 12 volts in the capacitor. I'm not going to get into joules and coulombs and all these different. I'm going to keep this in layman terms, put it in your terms. What you told an engineer when they first came up with flight, everything was, you had a word for it. It's named after barns and other things that you'd find on a farm. You know,
like he and ha, like what you would tell a mule to go left or right when you're plowing a field. Yeah, that kind of thing.
Yeah, and also a lot of the modern terminology was spin off of that. Well,
exactly.
So a capacitor paradox would be that, hey, look, okay, you had a load, and I actually built a working model of this up, and let's say you charge that capacitor to 12 volts, and let's say you got another capacitor that's the same value, that's completely discharged. Now you hook a load in it, and if you do a power under the curve, or you run, the load becomes part of the circuit to charge the other capacitor. It doesn't matter if it's a load that's only 1 or 2 ohms, or dead short, or a couple thousand ohms, or whatever. Doesn't matter how long it takes for the capacitor that's charged to pass through the load, whether it's quickly or over time. You wind up with 6 volts in each cap, and you're thinking to yourself, well, hell, there's my 12 volts, you know. And not only that, you created heat on that resistor when you ran through there, or if you had a little wheat bulb, you lit it up and the light dimmed out, then the capacitors leveled off. Okay. Well, technically, you did work with that 12 volts. And if you turn back around and take that capacitor and power the light directly with it, you can do a power run of the curve and go, okay, well, I had this many, electrons, however you want to look at it. Do a power run of the curve shows the power that came from the capacitor that ran through the light, and it's going to be just a curve, non-linear. It's going to go and curve out, and so most electrical engineers will tell you, well, look, if you do this, what you're talking about, if you charge a capacitor off a capacitor through the load, and then you discharge that capacitor through the load a second time, if you add both power of the curves up, it equals the first power of the curve if you just didn't use but one capacitor and run it through the load period. And they're absolutely right. Well, here's where all this goes south. Okay, if you got 8 ounces of water in a cup and you put that into half of that into a second cup, how many ounces of water do you have total?
You still have 8 ounces.
Okay, and minus the losses, which the losses would be the water that stuck to the side of the glass that you couldn't drip out with the drops. So we'll call that the losses in the inefficiencies of the components. Well, here's where that can slightly fall apart, or at least I think it does. I'm not going to say it's written in stone. Okay, you take a capacitor, you charge it up, you power a light bulb with it, you do a power run of the curve. You go, okay, well, this is my power. Well, that's just simple math formula to do that. And you go, okay, well, this is my area under here represents the power. Or you take a capacitor and you take that capacitor and you charge it up and you hook it to the power supply, you charge it up while it's powering the load, and then you got that power run to the curve, and then you discharge it, and it has another power run to the curve. Technically, if you add that up, it equals what the power supply originally gave up.
Right.
This is where the paradox comes on. Okay, well, if that's the case, how do you wind up with 4 ounces in this cup and 4 ounces in this cup? And this got me to thinking, I had actually built up a system, and we were buying true RMS meters. You were getting all this stuff, and the meters were getting better. And at first, I didn't know what I was doing when I was doing it. But when I was still working, before I had retired, I would go to my job after hours. You knew this. I had built something up that took a different approach with it, and I kept coming up with 130% efficiency. Not enough to make a closed loop with it, but damn sure enough to see it on the meters. And we're dealing with DC, although it was nonlinear waveforms, it was still DC. The meters were designed. As a matter of fact, I spoke with the engineers at Hewlett Packard when we bought these meters. I spoke to the engineers. I said, and told them these are the waveforms I want to measure. And they assured me, hey, look, if you can measure static on these meters, and it's going to give you true RMS power. I knew they were right about that. And so I built this thing up, and I thought, well, damn, man, okay, this is crazy. I'm coming up with this. I'm seeing this. Now, this is after you had got your information. Okay, well, this is, there's nothing there to spoof. But, I can't say that the people that wrote this up about the capacitor paradox took it through every regimen that they could to test it. And that was the problem I had. As a matter of fact, I will name one engineer by first name only. That we were dealing with 2 electrical engineers. One was a college teacher that taught people to be engineers. And he was the one that explained to me, look, monitor the voltage waveform and the current waveform. You got a 12-volt supply here. The capacitor you're going to charge is at 0 volts. Put a load in between that capacitor and the power supply. Turn it on. The capacitor technically is a dead short. As it charges, the light's at its full brightness, and it dims down in a non-linear wave in a fashion until the capacitor charges up to 12 volts. And he said, okay, now if you measured that power that came from the power supply to charge up, and then you turned around and you discharge that same capacitor that's got that 12 volts in it through the same light, and you do a second power run to the curve, that you will turn around and realize that all of it came from the power supply. And, of course, you did that by going, okay, 12 volts time the steps to the capacitor charging down. And of course, when you're discharging the cap, you don't have the 12 volts. It's non-linear. The voltage and the current are dropping at the same time. And
Right.
so I thought, well, I'm going to screw with this guy. So I took my power supply and I put a solid state relay in it so that the power supply, and by the way, I monitored the current draw on the power supply, because he was like, we have to go all the way back to the power company. I was like, well, we're going to do one
Right.
better than that. So I had a switch on it where I could flip it up, and the DC was either 100% on, or it was only on in impulses. That I did this. I did it like this, and what I was able to show him is, look, you're right with the formula, but if that's the case, I should see the power drop on the consumption of the power supply. Power supply is telling me that I took only this much power, and I blew his mind with it. As a matter of fact, by the time we built this thing up, because he was looking at me like, oh, let me tell you how it's done, son. And
Yeah.
granted,
Yeah.
so
Yeah.
I wasn't an electrical engineer, but
Yeah.
the
Yeah.
dude,
This guy was a
yeah,
triple E. Yeah.
okay,
Yeah.
but I go back to doing this. I was messing with electricity and learning about it when I was 6 years old, and I
Mhm.
can design, and I am technically an associate engineer now. Yes, I can design, but it's not something that I care to do. But I do it out of necessity for my own stuff. So to make a long story short, we built this device up, and the engineer had it. He was nice, but he was arrogant, like talking to us like, "Come here, children. Let me explain
Yeah.
this to you." So we went to
Yeah.
the college. He hooked it up, and he looked at us. He wasn't sure. He started questioning his own equipment. You remember this? So now
Yes,
he
I
goes,
do.
"We're going to go do this a different way." He said, we're going to split the test up in half." He said, "We had another a triple E engineer that said, I'm going to do the math on it." So we took it to the college. The college ran the power supply. He captured the voltage and current through time. He did it in a spreadsheet. And then we took the spreadsheet to a second engineer. And before it was said and done, the second engineer was going, well, man, this guy obviously did something wrong on his end. He's got to look at his equipment. He hooked something up wrong. He didn't do the test right. Well, the first engineer, his big claim to fame was he was part of designing power distribution systems, like for power companies, like for Hoover Dam
Yeah.
and
Yeah.
stuff like that. This
Right.
other engineer was a brainier genius too, that could do the same thing, but he took it in a different direction with computer and automation. But by the time it was all said and done, they went from calling this a power supply. Well, we need to talk to some other people. We're going to tell them, hey, man, that we got this box and we put this in it and we got this out of it. And that's where it ended with them. They
Yeah.
kind of like, well, the hell if we know what the hell is going on,
Yeah.
you know.
And we were the idiots, and they couldn't
Okay.
explain it. Yeah.
But it came down to that their calculations came damn close to, I think it was like 125 to 130%. Dude, that's
Yeah.
when I went back and this is before I had the meters, the correct meters to do it. When I
Right.
went back with we got all the meters so we could track stuff and true RMS meters. I came up with the same configurations and it came up with the same math. I was like, man, I'm coming up with 130%. To this day, I never have walked away from that. I still think there's something to it, but it's kind of like. Go
Yeah,
ahead.
you remember I had to do that power under the curve, that chart, that graph. We took a piece of graph paper
Oh,
and we had.
we did it with heat,
Yeah,
brother.
that's what it said. A 30% increase.
That showed 100. We did it with, and that was with Nick, a third engineer, a third electrical engineer that worked with who?
He worked with Texas Instruments. He was the Silicon Valley whiz kid.
And he was one of the people involved with the 555 timer.
Timer, yeah. I think most of that came out of his head.
As a matter of fact, he was the one that came up with build a bomb calorimeter, which for those out there, even if you do electronics or electrical, you may not know what this is. Basically, it's imagine using a thermos or something where you can control temperature and you put your electrical load in this thing. And on this thing, you also have a reference thermometer that measures the outside ambient temperature. this way you have you can do calculations down to the letter. Okay, what was the temperature of our inside of this thing where we're going to do the electrical test, because you heat it up with whatever power you're putting in it, and you watch the power under the curve cool down with it. You're doing it with temperature instead of voltage and current. And this tells you how much, you can get an idea how much power you produced. You can get a very accurate idea without using current and voltage calculations. And the outside thermometer, you use that as your reference. This also tells you this also gives you reference of, okay, how do I calculate losses or the instability of a room, which we didn't have to deal with that. Our room is stable, but we had it on there anyhow, just to make our tests more for real. I'm looking at the thing right now. I've got this thing and I've had it 20 years sitting over here. So we built a bomb calorimeter up. We did this capacitor test through it. You did the power run of the curve. Then we turned around and did it running it through the box. The box came up 130%. Nick then said, now we're going to produce hydrogen. And he said, so I built up another unit that had probes inside of it. And basically it produced oxygen and hydrogen. It was filled full of water. He said, this is foolproof too. He said, you charge your capacitor up. But that's what we use for a battery, a capacitor. We charged the capacitor up. We discharged it into this hydrogen producer. We measured how much gas was produced. And then we turned around and ran the capacitor as a battery through the box, and we produced more hydrogen. And I was like, well, okay, this is really freaking interesting. So we had two tests that proved that we got more out of what we put into it. The problem was, and where we sit today, it's not practical because we really can't do anything of any practical use with it, which is why I started throwing inductors into it, and I started getting really elaborate with it, but trying to keep it simple and keep this thing. I tried to make it into a power system where I could switch it quickly and make these things happen so that I could extract power from it and put this baby to bed, put it to rest once for all. And the last time I had tested it, I was putting out more than I was putting into it. I wanted to clean the system up and make it more user-friendly. I guess that'd be a word to put on it, to see if I could get more out of it that I'm getting. That's where I got it. I was really looking at headed to a closed loop system or something like that with it. Never got it there, but yeah, I think there was something done with it. I think we showed that there is an ability to get out more than you put into it, or make something incredibly efficient. But I think
it's what we did. Yeah,
my gut tells me we did a little bit more than that, but not enough to make this thing practical where it could be used for something. That's what I believe in my heart of hearts.
Yeah. Well, again, we're just dealing with, the modern technology and a lot of parts we're having to put together that really weren't the most efficient things in the world. I mean, we're trying, we're taking off the shelf stuff and trying to, modify it to make it where it'll work. And but the thing about it is, and I always like to try to look at the bright side of things. This project, even though it didn't really work out exactly the way I was hoping, it taught me so much about engineering.
It taught you about electronics. You know more about electronics than the average person does out there, unless somebody does it for a living. They do it for a living, that's different. But when it comes to the average person, you definitely know. I mean, most people don't know the difference in AC or DC or waveforms or any of that. So they're clueless on it.
Right.
But
exactly.
You don't need to have that I don't need to know what kind of waveform or what happens when I turn a light switch on. If I turn something on and it works, that's the end result. That's all you care about.
Yeah, exactly. But the point of it is, I mean, hell, it's just one of those things where we got the engineer's engineer. I mean, a guy that trains engineers, and he's sitting there kind of going, "Oh, I don't know what the hell's going on here, but it's not what you think it is," And
but it's not what he thought it was either, was it?
No, exactly. Exactly. I mean, we had him stumped. And this guy, and he was no idiot. This guy was super intelligent.
Hell no.
Yeah.
No idiot.
Yeah. So, but
Bill, as far as somebody that I've met in person. I mean, I can count engineers on, because I've worked with a lot of them, and I can count on the engineers on one hand. Um, out of over 40 years of doing this professionally, I can count all the engineers on one hand and not even use up all the fingers that I thought were just freaking exceptional. And
Oh
Bill
yeah.
was at the top of that pyramid. Other
I,
guys
I
I
would.
worked with were RF engineers because, of course, before I retired for the last 15 years, I worked strictly in RF and communication. And but that's a different story because I started off. I learned this by myself, electronics. It was something that was a bug for me, and I wound up going to before I knew you. I wound up going to work in television shops. I was working on televisions when they were tubes, and
Yeah.
I learned to repair televisions as far as back as 1968. That's how far back I go. I would go get
Oh shit.
no shit, dude. I'd get televisions off tube televisions off the side of the road. People were throwing them out, and I had televisions that people throw out the like 1955 television. Finally went out
Yeah.
on them. They set it on the curb. Brought it. My parents raised hell. What is this junk you're bringing here? And just by going to the library and understanding the basic functions of it, um, I was able to understand how the television worked, what it was supposed to do,
Hmm.
and I was able to fix power supplies in them, realign tuners and stuff like that. And every room in our house had a television in it. They're all black and
Hmm.
white. And my parents were like, oh, look what he can do. This guy can fix, And then when I took electronics when I was in high school, um, when I through the tech classes, my last couple of years, and then I got on this job training. I did electrical for a while, and then I went to work in a television shop, and I stayed in television. Between that, because man, like I said, I'm a guy that wears many hats, and many things interest me. You know that. I mean, hell, I traveled full time, playing music professionally. I did that all my life, and so in between
Right.
doing all of that, I was doing working. I'd always had a job. When you got a skill like that, you always have a job. I'd come off of the road. We take 2 weeks or 3 weeks off from traveling. I would come back, television shops, it's like, hey, would you like to come in and make some money? Yeah. And if I wasn't with a band traveling, or if I was playing locally, my ass was working full time repairing television, microwave ovens, VCRs, you name it, I did it. And that time I wasn't engineering. That didn't happen until I got into RF and started working in communications. And then all of that was design. I was doing a lot of passive design for the cable industry, and a lot of the stuff I designed is kind of funny. It's still out there to this day, still being used. Some of the stuff I designed, but I worked
Yeah.
other under engineers and find out. I became an associate engineer, and I did all the grunt work for them. They did the line amp work and stuff like that. I did all the filtering and EQ design, but I could also work on line amps and do all that with them. But it was my introduction, excuse me, to work with CAD programs and designing on CAD and stuff like that. So it all paid off. But going back to
Right.
the stuff you and I did, man, I mean, man, I think of all the crap we did. The Bedini motor, um, that was one of the things. Oh, there's so many. I just lost count. I got so much stuff here. It's off the charts. I found old papers and stuff here where you would order stuff and it was Xeroxes of stuff. People say like, "Oh yeah, I'll build this up. You'll be
Yeah.
off the power grid forever." A lot of it was just total rubbish.
Right.
Because you didn't have an internet back then. Uh, Speaking of the internet, man, and I'm sure this has got to be a three-letter agency doing this. A lot of people originally were putting stuff out. They would get up there and experiment, as I had mentioned, the Muller motor, and people
Right.
put other stuff up there, uh, other stuff out there. Wits Industries, all these people try to put all this stuff out where they're building closed loop systems or stuff like that. And now, dude, you can't, if you type in over Unity on YouTube, it's all a freaking joke. It's
Yeah.
all, it's
A
it's
clown
like
show.
it's a
Yeah.
clown show. It's no, don't insult
No insult
clown shows.
clowns. Yeah. Yeah.
But it's just the stupidest bullshit you ever wanted to see, and it really pisses me off because
Right.
it should have been a good tool for people to be able to go get information. I mean, I got the gasifier stuff off there. I got the Muller motor stuff off there. Man, YouTube has been a classroom for me. And speaking of that, you can find college courses that you can replay from the beginning to end on physics, electrical engineering, electronics, plumbing, you name it, man. You type it in there, you can find it, dude. When we put the extension to my shop out here, I went on YouTube and self-taught myself. Took me a day to do it in vinyl siding. And when I went out there and done it, there wasn't any questions of how I had to cut it, what I had to measure. And when I was done with it, it looked like I paid somebody to come out here and do this shit for me.
Yeah,
And
exactly.
so YouTube to me is a playground of a wealth of information.